In section 3.5, we look at rational functions, including notation for infinite behavior of such a function. We'll identify the vertical, horizontal, and slant or oblique asymptotes of a rational function. We'll learn how to graph it and see some of the applications of a rational function. So the first question, of course, is what's a rational function? So we say that a function in the form of f of x equal to p of x divided by q of x is a rational function where both the p of x and the q of x are polynomials. So if you have a polynomial divided by a polynomial, then that is a rational function. Now the domain of a rational function, let's say domain of f of x, the rational function, is the set of x's where q of x is not equal to 0. And remember that q of x is going to stand for the denominator of this rational function. So any place where the denominator is not 0, then that is a number that's in the domain of the rational function. That's nothing new than anything that we've already done before. You have a fraction, set the denominator equal to 0, and exclude those x values where it is equal to 0. Example number 1. Find the domain of each rational function. F of x is equal to 3x minus 1 over x plus 5. So we'll set the denominator equal to 0 and solve for x. And we get x is equal to negative 5. If I graph the domain on a number line, then we have an open circle at negative 5. And we get graph on the left side and on the right side. And if I write the domain in interval notation, then it goes from negative infinity to negative 5, union negative 5 to infinity. And if I write it in set builder notation, it'd be the set of x's such that x is not equal to negative 5. That's the domain. That's the set of x's that we can use inside this function. Let's look at part B. G of x is equal to x over x squared minus 3x minus 10. So again, we look at the denominator and we set it equal to 0, and we solve for x. So I'm going to factor. I get x and x, 5 and 2, with a negative 5 and a positive 2. So the zeros of the denominator are x equals 5 and x equals negative 2. If I draw this on a number line, I have an open circle at negative 2 and an open circle at 5. And everything else gets shaded in. One strategy that you can use to help you when writing the intervals is to number the intervals that appear in the number line. There's 1, 2, 3 intervals in my number line that are split up by the open circles. Since there are 3 intervals shaded, there need to be 3 intervals listed in the domain when you write it in interval notation. The first interval goes from negative infinity to negative 2. Then union, we jump over negative 2 and go negative 2 to 5. That's the second interval. Union, the last interval, goes from 5 to infinity. In set builder notation, this would be the set of x's such that x is not equal to 5 or negative 2. Let's take a look at part C. J of x is equal to 8x squared minus 1 over x squared plus 9. Again, we have a rational function. To find its domain, we take the denominator and set it equal to 0. Solving for x, I have x squared is equal to negative 9, but we're only using real numbers, and so x squared cannot be equal to negative 9. So we have no real solutions. That means there are no restrictions on the domain of the function. So the set of x's where I can evaluate this function j is the entire real line. Next, let's look at some notation. This notation with the arrow stands for approaches, and we use it to see how the x values are approaching certain numbers or certain areas of the graph. This first one, x approaches c from the right. So the little plus superscript here means from the right. So let's write this entire statement. This means x approaches c from the right. Now, one thing to note is that this also implies that the x is not equal to c at that point. We just want to know the x's are going towards c, but they're starting on the right side of where x is equal to c. Similarly, if you have a superscript of a negative, that means from the left side. So we say from the left. And this is x approaches c from the left. And again, the x is not equal to c, but it is less than c and approaches c from the left side of c. And we'll see an example of all this in a second, so hold tight. Next, we have x approaches infinity. That means x approaches infinity. And it means that the x values are increasing without bound, meaning they just get bigger and bigger and bigger. And then we have x approaches negative infinity. Which means the x values are decreasing without bound. So let's take a look at some examples. Example number 2 says, let f of x be equal to the function that's 1 over x. That's a rational function. 1 is a polynomial. It's not a great polynomial, but it is a polynomial. And of course, x is a polynomial. So f is a rational function. And then here we want to do these 4 parts. So the question is, as x approaches 0 from the right. So here I'm going to trace out the x's going towards 0 from the right. The next part is f of x approaches blank. So the question is, what happens to the y values of this rational function as the x's get closer and closer to 0 coming in from the right side? Well, here you can see that the y values are getting larger and larger and larger, and they are not going to stop. They're going to continue to increase as we get closer and closer to 0 from the right. So the f of x values are going to approach positive infinity. Part B is the other side. As x approaches 0 from the left, what happens to the y values? What do the y values approach? Well, here you can see as the x's are approaching 0 from the left side, tracing along the graph, you see that the y values are going down, and they keep going down the closer and closer you get to x equals 0. So therefore, the y values are going to approach negative infinity. Part C, as x approaches positive infinity, what do the f of x values do? So here, if you continue going to the right without bound, the curve gets closer and closer to y equals 0. So we say that f of x approaches 0. And part D, as x approaches negative infinity, what does f of x approach? Again, as x approaches negative infinity means that we're going to the left side, and the x values are decreasing without bound. So f of x is also approaching 0 here on the left side of the graph. The last example hinted about two aspects of rational functions. They are the vertical asymptotes and the horizontal asymptotes. A vertical asymptote is defined as such. The line x equals c is a vertical asymptote of a graph of a function f of x if f of x approaches infinity or negative infinity as x approaches c from either side. So in other words, suppose that we have a graph, and here's an x value that is x equals c. Then if the graph is approaching positive infinity on the left side, then we can say that x equals c is a vertical asymptote. Similarly, it could be approaching x equals c from the right side and go up to positive infinity. Or it could be approaching from the left side and going down to negative infinity. Or it could be coming in from the right side, going down to negative infinity. All of these situations imply that the vertical line x equals c is a vertical asymptote. So don't forget to write your lines as vertical lines, x equals a number. Now, how do you find the vertical asymptotes of a rational function? First, you want to reduce your rational function to lowest terms and write it as a rational function f of x is equal to p of x over q of x. This just means that you should try to factor your rational function and cancel common factors as the first step, and then use only the reduced form of your rational function. Then, step 2, take the remaining denominator, q of x, set it equal to 0, and solve for x. The real solutions to this equation are the vertical asymptotes. So here's example number 3. Find the vertical asymptotes of f of x is equal to 5 over x plus 3. This one is already simplified, so now I'm going to take the denominator, set it equal to 0, and solve for x. I get x is equal to negative 3, and that's a vertical asymptote. That's it. Example number 4. find the vertical asymptotes of m of x is equal to x plus 9 divided by x squared minus 81. So first I need to simplify if possible. So notice that the denominator factors. It factors as x plus 9 and x minus 9. I can cancel the x plus 9s. Don't forget to leave a 1 in the numerator as a placeholder. The reduced rational function is now 1 over x minus 9. You take this new denominator, x minus 9, set it equal to 0, and solve for x. And we get x is equal to 9. And that's the only vertical asymptote. So the question that we get a lot is any point that is not in the domain of a rational function automatically a vertical asymptote? And the answer is no. The answer is no. Here we can look at the domain of the original m is the set of x's such that x is not equal to 9 or negative 9. But the vertical asymptotes of m are just x equals 9. So the question is, what happened to negative 9? Well, the negative 9 is the number that came out when we canceled the common factors of x plus 9 in the top and the bottom. And it turns out when you can cancel factors like that, you create a different structure on the graph called a removable discontinuity, but we just colloquially call it a hole, because the graph at negative 9 is in fact some kind of hole. Looks like that. It's an actual hole in the graph. Example number 5. Find the vertical asymptotes of p of x is equal to x minus 7 over 2x squared plus 5x plus 2. So this one is already reduced. So we set the denominator equal to 0. And we factor. This factors as 2x plus 1 times x plus 2. Set each factor equal to 0 and solve, and you get x equals negative 1/2 and x equals negative 2. And those are the vertical asymptotes. Another type of asymptote is the horizontal asymptote. The line y equals d is a horizontal asymptote of the graph of a function f of x if f of x approaches d as x approaches positive infinity or negative infinity. So just like before when we had these graphs here, we could say that d is a horizontal asymptote if the line the function comes closer to the line as we move toward negative infinity, or as the graph moves closer to that line, positive infinity. And it can be from above, or it can be from below. It just has to get closer to that line as the x's move closer to infinity or negative infinity. And this is a type of end behavior. It's a different end behavior than what we studied for polynomials. It is part of the end behavior pattern for rational functions. So how do you find the horizontal asymptote of a rational function? Well, you start with a rational function. F of x is equal to p of x over q of x. The p stands for the numerator, the q stands for the denominator. And what you want to do is you want to look at the degree of the polynomials in the numerator and the denominator. Reminder that degree of a polynomial is equal to the highest power. It's not necessarily the first power listed, but it's the highest power of that polynomial. So if, number one, if the degree of the numerator is smaller than the degree of the denominator, then the horizontal asymptote is automatically y equals 0. Number two, if the degrees are the same, then the horizontal asymptote is equal to the lead coefficient of the numerator divided by the lead coefficient of the denominator. And remember that the lead coefficient is the coefficient of the term that gives you the degree. So it's the coefficient in front of the x with the highest power. And then part 3 is if the degree of the numerator is bigger than the degree of the denominator, then there's no horizontal asymptote, but if the degrees are 1 apart, then you get a slant asymptote. Now, it is true that rational functions can only have one horizontal asymptote, but that's not true for other functions. Other functions could have one on one side and a different one on the other side. Example number 6. Find the horizontal asymptote of f of x is equal to x plus 4 over x squared minus 3x plus 8. So we look at the degrees. So the degree of the numerator is 1, because that's the highest power on the x's. The degree of the denominator is 2, because it's quadratic. And when the numerator's degree is smaller than the denominator's degree, then the horizontal asymptote is automatically y equals 0. Example number 7. Find the horizontal asymptote of f of x is equal to 3x squared minus 3x minus 4 over 8x squared plus 9x plus 1. So let's look at the degree of the numerator. It's a quadratic, so the degree is 2. Let's look at the degree of the denominator. The denominator is also quadratic, so it's also a 2. And when the degrees are the same, then the horizontal asymptote is found by taking the ratio of the lead coefficients. The lead coefficient of the numerator is 3, and the lead coefficient of the denominator is 8. So the horizontal asymptote is y equals 3/8. Example number 8. Find the horizontal asymptote of f of x is equal to x squared minus 3x plus 5 over x minus 1. So again, we compare the degrees. The degree of the numerator is 2. The degree of the denominator is only 1. So when the degree of the numerator is bigger, then we don't have a horizontal asymptote. So there's no horizontal asymptote. But what do we have? Well, since the degrees are off by 1, we have what they call a slant asymptote, or also known as an oblique asymptote. And to find the slant or oblique asymptote, you actually need to perform the division of the rational function. You can use synthetic division if it is possible, but if it's not possible, use long division. So use synthetic division if possible. Long division otherwise. So here, because the denominator is in the form of x minus a number, I can use synthetic division. So we'll have the 1 on the outside. We have 1, negative 3, and 5. Bring down the 1. 1 times 1 is 1. Negative 3 plus 1 is negative 2. 1 times negative 2 is negative 2. 5 minus 2 is 3. We don't really care about the remainder in this case, but the slant asymptote is y equals, and then we reform this line right here. So that would actually be x minus 2. And contrary to popular belief, a function can cross an asymptote. In particular, it can cross the horizontal asymptote somewhere in the middle of the graph. So what really is an asymptote? Well, it's just a guide for how the function is behaving. The horizontal asymptotes tell us what values the y value approaches as you get further and further away from the center, when x goes to infinity or x goes to negative infinity. Example 9. Find the point where the rational function f of x equals x squared minus 3x minus 2 over x squared plus 1 crosses its horizontal asymptote. So first, let's find the horizontal asymptote. Let's take the degree of the numerator, that's 2, and then the degree of the denominator, which is also 2. And since they are equal, that means the horizontal asymptote is equal to the ratio of the lead coefficients. Well, this is just 1 over 1, which is 1. Now, in order to find where the function crosses its horizontal asymptote, we're essentially finding what x value has the value of y equals 1. So we're going to set f of x equal to 1 and solve for x. So this is x squared minus 3x minus 2 over x squared plus 1. Set that equal to 1. It's this one right here. To solve this, I'm going to cross multiply. And we get x squared minus 3x minus 2 is equal to x squared plus 1. The x squareds cancel. That leaves me with negative 3x is equal to 3, and x equals negative 1. So the point where it crosses its horizontal asymptote is -1, 1. The x came from the solution, and the y is equal to 1 because that's what the horizontal asymptote number is. Next, let's look at some steps to graphing a rational function. So first, start with a rational function in lowest terms. Number 1, find the x and y-intercepts. Number 2, find the vertical asymptotes if it has any. Number 3, find the end behavior, which would be the horizontal or the slant asymptote. Number 4, find where it crosses its horizontal or slant asymptote. And then number 5, plot the points in the intervals separated by the x-intercepts and the vertical asymptotes to get sort of a general feel about what the graph should look like. Example 10. Graph f of x equals 2x minus 6 over x plus 2. So our first step is to find the x-intercepts. The x-intercepts are when y is equal to 0. So that means I'm going to take the function and set it equal to 0. Then I'm going to multiply both sides by this denominator to cancel it off. This is the same as cross multiplying. So this cancels over here, and the left side gives me 2x minus 6. The right side is 0 times x plus 2, so that's still just 0. So here's a little shortcut that you can take in the future. In order to find the x-intercepts of a rational function, all you need to do is set the numerator equal to 0. The denominator is not going to matter as long as you already have it reduced from if there were factors that could cancel. As long as you have it reduced, then this will work every time. Solving for x, I get 2x equals 6 and x equals 3, so that gives me the point 3, 0. Let's find the y-intercept. The y-intercept is when x is equal to 0. So we're going to have f of 0 is equal to 2 times 0 minus 6 over 0 plus 2. You work that out and you get -3. All right, step 2 was to find the vertical asymptotes. So I look at the denominator and I set it equal to 0. I get x equals -2. So x equals -2 is a vertical asymptote. Step 3 is to find the horizontal asymptote. So I look at the function. I have a degree of 1 in the numerator, and I have a degree of 1 in the denominator. Since these are equal, then I know that the horizontal asymptote is the ratio of the lead coefficients. So that would be y equals 2 over 1, which is 2. So y equals 2 is my horizontal asymptote. Step 4 is to find where the graph crosses its horizontal asymptote. So I'm going to take the function 2x minus 6 over x plus 2, and I'm going to set it equal to the y value of the horizontal asymptote, which is 2. Then I will solve. I'm going to multiply both sides by x plus 2. And we get 2x minus 6 is equal to 2x plus 4. The 2x's cancel. That gives me negative 6 is equal to 4. That is false. That's not true. So there is no solution to where the function is equal to 2, which means that f does not cross its horizontal asymptote. So it can cross it, it's just that this one didn't. And now step 5 is to get a general sense of where this function lies. Is it above or below the x-axis? To do that, we're going to use a number line. And on the number line, I'm going to put in my vertical asymptote of negative 2. And I'm going to put in my 0 of x equals 3. We use VA and a little 0 above the negative 2 and 3 respectively to denote that this is where the vertical asymptote is and this is where the 0 is. Now what we understand is that the only place that a function can cross its x-axis from being positive to negative or negative to positive, if it's a rational function, is when it passes over its vertical asymptote or when it actually passes through the x-axis by being a 0. So negative 2 and positive 3 are the only places where it can change sign. And now I just need to figure out what those signs are. So we're going to do some testing. And what you do is you pick numbers in the interval to test what these values are. So I'm going to pick a number between negative infinity and negative 2 to test this first interval. I'm going to choose negative 3. So f of negative 3 is equal to 2 times negative 3 minus 6 divided by negative 3 plus 2. This is equal to negative 12 over negative 1, which is positive 12. It doesn't really matter what the number is, but what I do want to know is if it's positive or negative, and it's positive. So I'm going to fill this piece of the graph up with positive signs to indicate that at x equals negative 3, the graph is positive, but more importantly, for the entire interval from negative infinity to negative 2, the graph is above the x-axis. Next, let's pick another number between negative 2 and 3. I will pick 0 because I've already computed that one. F of 0 is equal to negative 3. That's the y-intercept. And so now I know that at x equals 0, the y value is negative 3. But that means that every value of the function where x is between negative 2 and 3 is also negative, because there's no place for it to change over. And finally, let's pick a value between 3 and infinity. I will pick 4. Now we test f of 4. We get 2 times 4 minus 6 over 4 plus 2. That would be 1/3. But that's positive, and so we'll put positive symbols up here. So now we know exactly where the graph is. Between negative infinity and negative 2, the graph is above the x-axis. Between negative 2 and 3, the graph is below the x-axis. And from 3 to infinity, the graph is again above the x-axis. So let's go ahead and put all this together and draw a graph. And here's what we know. Number 1, we know that there is an X-intercept at 3. And we know there's a Y-intercept at negative 3. we know that there is a vertical asymptote at x equals -2. We draw in our vertical asymptotes using dashed lines. We know that there is a horizontal asymptote at y equals 2. And now we complete the graph. So we know that on the left side, as x goes toward -infinity, the graph has to get closer and closer to the horizontal asymptote. But we know that it can't cross it, because if it could cross it, we would have gotten a result when we tried to find where it crossed. We also know that the graph is entirely positive, in other words, above the x-axis, on the left side of x equals -2. That means that the graph of the function has to be above the horizontal asymptote. And as we move to the right and get closer and closer to x equals -2, it has to go up. If it were to go down, it would necessarily have to pass through the x-axis and produce an extra 0 that we don't have. So it's impossible for it to go down at that point. It has to go up. Crossing over to the right side of x equals -2, we see that the graph is negative based on this sign right here. So we know that it is down at the bottom. And we know that it's going to rise. It's going to pass through these intercepts. And then it's going to get closer and closer to the horizontal asymptote as it moves out toward the right. It never crosses the horizontal asymptote. We proved that already. But it does get closer and closer. It also, we proved that it does cross through this X-intercept by looking at the sign chart, because it became positive immediately after 3. And so there it is. There's the graph. Let's look at example 11. Graph g of x is equal to x squared plus 3x minus 4 over x squared minus 2x minus 8. So our first step is to find the x-intercepts. The x-intercepts are when the function is equal to 0, but the shortcut trick we can use here is just set the numerator equal to 0. This factors as x and x, 4 and 1, with a positive 4 and a negative 1. So x is equal to -4 and x is equal to 1. Then we need to find the y-intercepts. This is when x is equal to 0, so essentially we want g of 0. So that would be 0 squared plus 3 times 0 minus 4 over 0 squared minus 2 times 0 minus 8, which is 1/2. Step 2, find the vertical asymptotes. So to find that, we're going to set the denominator equal to 0. This factors gives me x and x, 4 and 2, with a -4 and a +2. So x is equal to 4 and x is equal to -2. Step 3 is the horizontal asymptote. We look at the degree of the numerator and the degree of the denominator. We notice that they're both 2. So the horizontal asymptote is the ratio of the lead coefficients. That's 1 over 1, which is 1. So it's y equals 1. Next, we want to use that information and determine if this graph crosses its horizontal asymptote. So we're going to take the function g of x and set it equal to the horizontal asymptote number, which is 1. So this would be x squared plus 3x minus 4 over x squared minus 2x minus 8, and we set that equal to 1. Cross multiply, we get x squared plus 3x minus 4 equals x squared minus 2x minus 8. X squareds cancel, but I still have x's, so we are going to get a solution here. 3x, move the negative 2x over as a positive, and we get 5x. We have negative 8, move the negative 4 over as a positive. Those add together to give us negative 4. So x is equal to negative 4/5. So therefore, there is a point on the graph at negative 4/5, comma 1, where this graph passes through that horizontal asymptote. Finally, let's do a little sign chart to see what the graph looks like, whether it's above or below the x-axis at each of these different points. So I'm going to pull together the zeros, or the x-intercepts, and the vertical asymptotes. I'm going to put them all in order on the number line. So I'm going to have negative 4, negative 2, 1, and 4. Negative 4 was an x-intercept, or 0. Negative 2 was a vertical asymptote. 1 was a 0. And 4 was the other vertical asymptote. Next, I'm going to pick test points to test each of these intervals. So the first one is going to be negative 5. So I need to find g of negative 5. And if you work that out, you get 2/9, which is positive. So we're going to have a bunch of positives here. Next, I want to work out negative 3. G of negative 3 is equal to negative 4/7. So that's a negative. And so there's negatives in between negative 4 and negative 2. Between negative 2 and 1, I'm going to test 0. And g of 0 is 1/2, as before. And that's a positive. So the graph between negative 2 and 1 is above the x-axis. Between 1 and 4, I'm going to test the point x equals 2. That's going to give me negative 3/4, so that's a negative. And then finally, I'm going to test at x equals 5. And so g of 5 is equal to 36/7, which is positive. And now we know what the graph should look like based on this. So let's go ahead and dissect a little bit of this. just from this chart right here. I want to point out that when you look at these that are marked as vertical asymptotes, you can tell what the graph is going to do based on what the signs of the graph are on the left and the right. So for example, here at x equals -2, we have a vertical asymptote. And the graph on the left side of that is negative. So that means the graph is going to come in and it's going to go down to -infinity, because it has to go to either +infinity or -infinity. And if it's negative on the left side, then that means it's going to be going down. On the right side, the graph is positive, meaning it's above the x-axis. So therefore, it's going to be above the x-axis. And so as we get closer to x equals -2 on the right side, it goes toward infinity as it gets closer to the vertical asymptote. And the same type of behavior is true over here on this other one. So that's how you use the sign chart to determine what the graph looks like with respect to its vertical asymptotes. Let's go ahead and make a graph. All right. We have several points to put down. So first, I'm going to go ahead and put down -4. And -4 was an X-intercept. And we also have 1 is an X-intercept. We have a Y-intercept at 1/2. We have a vertical asymptote at x equals 4. And 1 at x equals -2. And we have a horizontal asymptote at y equals 1. We have a point on the graph at -4/5, 1. That's the point where the graph passes through its horizontal asymptote. When we look at the sign chart, we see that as x goes to -infinity, we approach the horizontal asymptote, and we can't cross the horizontal asymptote because that would be a point that we found in step 4. But we also have to get close to x equals -4 and pass through that point. So therefore, the graph is going to be below the horizontal asymptote, pass through x equals -4, and then from -4 to -2, the sign chart says that the graph is negative. So it's going to come down and go down toward -infinity as we get closer and closer to -2. On the other side of -2, the graph is positive. So it starts up at +infinity, and it comes down. It passes through these 3 points that we found, and then it continues and goes down toward -infinity. As we cross over x equals 4, then the graph starts high again at +infinity. Comes down and then settles in on the horizontal asymptote as it goes toward x equals, or as x goes toward infinity. And that's the graph. Let's look at example 12. Graph h of x is equal to 2x squared minus 2 over x minus 3. So step 1, let's find the x-intercepts. So I'm going to take 2x squared minus 2, set that equal to 0. So that's 2x squared is equal to 2. Then x squared is equal to 1. So x is equal to plus or minus 1. So there's two different x-intercepts, one at plus 1, one at minus 1. Next, let's find the y-intercept. That's when x is equal to 0. So I'll plug in h of 0. So it would be 2 times 0 squared minus 2 over 0 minus 3, which is 2/3. Step 2, find the vertical asymptote. So we take the denominator, set it equal to 0, and solve for x. So it's x equals 3. Step 3, find the horizontal asymptote. But if we look at the function, it's 2x squared minus 2 over x minus 3. So we have the degree on the top is bigger than the degree on the bottom. So that's not a horizontal asymptote. That's going to be a slant asymptote. And the way we find the slant asymptote is by doing division. So now we do the synthetic division. And so we have 3 on the outside. The coefficients of the numerator are 2, 0, and negative 2. The 0 is there because there is not an x term. Now we bring the 2 down. 3 times 2 is 6. 0 plus 6 is 6. 3 times 6 is 18. And 18 minus 2 is 16. So the slant asymptote is y equals 2x plus 6. Step 4, we want to find out if the rational function actually crosses its slant asymptote. So I'll take the expression of the slant asymptote, 2x squared minus 2 over x minus 3, and I'm going to set it equal to the expression for the slant asymptote, 2x plus 6. Cross multiply. And we get 2x squared minus 2 is equal to 2x plus 6 times x minus 3. Multiply out the right side, and the right side becomes 2x squared minus 18. The middle terms cancel. The 2x squares cancel, and that leaves me with 0 equals negative 16, which is false, which means there's no solution, which means there is no crossing of the slant asymptote. So that means it's always, this graph is always on one side or another of the slant asymptote, depending on how it's affected by a vertical asymptote and such. But it'll never cross through the slant asymptote. All right, let's make a sign chart. So in my sign chart, I'm going to put down both of my x-intercepts, so -1 and +1. And I'm going to put down my vertical asymptote at 3. So vertical asymptote, my zeros. And then we'll test this at -2. So h of -2 is equal to -6/5, and that's negative. So it's all negative here on the left side. I'll test this middle interval at 0, and h of 0 was equal to 2/3. And that's positive. We'll test this interval between 1 and 3 at x equals 2. And h of 2 is equal to -6. That's negative. And then we'll test this last interval at a number greater than 3, which is 4. H of 4 is equal to 30. That's a positive number, so these are all positive. So again, this tells me how the graph behaves at the vertical asymptote. It's going to go down on the left and up on the right. So let's make a graph. So we're going to have an X-intercept at -1 and at +1. We have a Y-intercept at 2/3. We have a vertical asymptote at x equals 3. We have a slant asymptote with y equals 2x plus 6. 3, 4, 5, 6. So it's going to go through this point right here, and then it's going to go through this point here, up to over 2. So this may not work out very well. So there's the slant asymptote. So I'm going to go ahead and extend my vertical asymptote here, like so. And that's it. So now we're ready to graph. So looking at the sign chart, on the left-hand side, we see that the graph is negative. And I see that I need to get back to the points where x is equal to -1 and +1. And I can't cross the slant asymptote. So I have to be below the slant asymptote. Then come in, hit these points here. And then I have to go back toward the vertical asymptote. And as I get closer and closer to x equals 3, we see that it's going to go down toward -infinity. So it goes down like that. As we cross the vertical asymptote, the graph on the other side is positive because we have positives in the interval from 3 to infinity. So it's going to be above, and it's going to start up here at infinity. And then as it continues going to the right, it has to sort of curve back toward the slant asymptote. So it's going to sort of bend back around this way, and then it's going to get closer and closer to the slant asymptote as it heads off toward x goes to infinity. So it does that little bin-like shape right there. All right, that's it for this section. Thanks for watching.